My name is Samuel Fromer, and I'll be presenting transport of algebraic structure to latent embeddings. I'll start by motivating our approach using the importance of sets in robotics and controls. For example, we might want to predict the trajectory of an agent and a corresponding uncertainty set. In manipulation, we might want to reason about the volume of space that is swept through by a manipulator, and so on and so forth. However, if we try to apply machine learning models to these problems, we often run into issues with the pointwise nature of neural networks. What if instead we could parameterize a model that acts natively over subsets of Euclidean space, as shown here? One reasonable way of accomplishing this is to leverage implicit neural representations. Consider this circular subset of R2. An implicit neural representation is just a network G parameterized by phi, which is trained such that the superlevel set of the network is the original set of interest. We can train many such INRs over a variety of sets and use those to train an autoencoder style architecture, which takes these parameters phi and maps them down to a compact latent representation Z. These compact representations are useful for a wide variety of downstream applications, some of which I highlighted previously. However, all these applications are likely to leverage basic set operations, such as union and intersection. So we would like to have a consistent way of learning these operations in the latent space. Informally, what I mean is if we have sets A and B in the original set space, we want that the union of these two sets in the set space to be approximately equal to taking the sets, compressing them into the latent space, taking a learned union operator there, and then decoding. This sets up our main problem, which is how can we learn operations in this latent space which provably obey algebraic laws? For example, consider this cup, which might have two implicit neural representations, one for the handle and one for the bowl, and say we want to take the union of these two solids. Intuitively, we know that in set space, A union B should be the same as B union A. How can we learn a latent space operation which satisfies the same law? For commutativity, there are some ways of doing this. However, this becomes a much more difficult problem for properties such as associativity and distributivity. While I've been using sets to illustrate, the same principle applies to a wide variety of objects with algebraic structure. In the middle here, I have functions from R2 to R, and on the right-hand side, I have probability distributions. All these objects live in spaces endowed with algebraic operations, such as addition, and laws, such as commutativity. Additionally, elements in each of these spaces can be learned using off-the-shelf machine learning models. And then there are existing approaches to compress these down into latent spaces. And the overarching question here is, how can we learn latent space operations which provably satisfy the algebraic laws in the original mathematical space? A careful exposition of our method requires tools from universal algebra, so I'll just give the high-level intuition here. On the left-hand side here, we have the source algebra, in our case sets, which have elements such as the subsets of R2, operations like union and intersection, and laws such as commutativity. We want to ultimately define corresponding operations in this latent space here in the top right. To do this, we first design a mirrored algebra whose underlying space is a Euclidean vector space of the same dimensionality as the latent space. Then in this space, we hand design one operation for each operation in the original source algebra. This operation is a nice closed form arithmetic expression which takes in the same number of arguments as the original operation in the source algebra. For example, if we have a union operation in the source algebra, in the mirrored algebra we might pick the corresponding union operation to be element-wise maximum, which is also commutative. The last step here is to learn a bijection phi between these two spaces, and then we can define the operations on the latent algebra as just taking two elements in the latent algebra, mapping them via phi to the mirrored algebra, doing the corresponding operation, and mapping back via phi inverse. In our paper, we proved that this construction, if we pick the mirrored algebra correctly, allows us to learn latent space operations which provably satisfy algebraic laws. We validate our approach in a controlled setting where we are learning the union and intersection operations over a dataset of synthetic two-dimensional polygons. We compare a range of mirrored algebra operation choices, each of which corresponds to one orange dot on this plot on the right. Different choices of mirrored algebra operations satisfy a different number of algebraic laws, shown here on the x-axis. These results support our main hypothesis, which is that as operations satisfy more algebraic laws, they generally yield superior performance.